Now, as we talked about before, OSPF is just another option for routing, for dynamic routing. OSPF stands for Open Shortest Path First. It originally was released in 1991 by IETF, and then updated in 1999 as well as 2008 to include OSPF version 3, which is OSPF for IPv6. All right, it is a link state routing protocol, as we mentioned before, and as such, it has a much more detailed understanding of the network topology, but as such, it requires more processing power, it requires more CPUs, it's a little bit more complex to implement, a little bit more memory required as well. All right, so we're going to do pretty much the same thing with OSPF that we did with EIGRP. We're going to talk a little bit about some of the theory of OSPF. We're going to do an OSPF implementation lab, and then we're going to wrap up the chapter by talking about all of the OSPF properties and looking at routes and whatnot. We're not going to do it in quite as much detail as we did with EIGRP, but we will talk about a lot of the high-level aspects of OSPF. We're also only going to do OSPF for IPv4. We're not going to do any IPv6 in this case. It's pretty much the same as EIGRP with regard to IPv6. So, here's the first major difference between OSPF OSPF and EIGRP. In EIGRP, we run the network as a flat network, meaning that every single router is in the same autonomous system. Now, OSPF also has an autonomous system. In fact, the entire OSPF domain is called the OSPF autonomous system. So this is all the autonomous system. But within OSPF, we also have the ability to run these subdomains called areas. Now you can implement OSPF as a single area design, which is what we're going to do in our lab, or you can run OSPF in a multi-area design. What do you think the benefit of multi-area design is? Well, one of the benefits is if I have a bunch of contiguous networks here in this area, I can summarize those routes into the backbone through this router, which is called an ABR, Area Border Router. Area Border Router is a router that has interfaces in more than one area. The same thing with Area 51. A bunch of routes. I can summarize those routes into the backbone. So by having this hierarchical structure, I can reduce the overhead in the backbone by having these summary routes. Now, that of course is going to introduce some complexity in the design, because you're going to have different route types. They're called LSAs. You're going to have different route types and so on. There are also some restrictions to multi-area design. And the restrictions include, first of all, area 0 has to be contiguous. You can only have one area 0. And then all of the non-backbone areas have to be directly attached to the backbone. You can't have area 10, area 11, area 12 to go to area 0. All of these areas have to be directly attached to the backbone. All right? Because we don't focus a whole lot of attention on multi-area design, that's about all I'm going to say about that. We'll see maybe a little bit more throughout the chapter, but for the most part, our focus is going to be on single area OSPF, which you guys will be thankful for, because when you start to get into multi-area design, things get a little bit more complicated, particularly with OSPF. But I'll defer that stuff to the CCNP. So we have a neighbor table, just like EIGRP. We have a topology table, just like EIGRP. We have a routing table, just like EIGRP. These are the three data structures in OSPF. What goes into the neighbor table? A list of all my active OSPF neighbors. What goes into the topology table? Everything that I learned from those neighbors. It's called a linked state database. And what goes into the routing table? My best routes. Right. My best routes go into the routing table. There are 5 packet types in OSPF. We know what a hello packet is already. We talked about that. What about a linked state request? A linked state request is like what in EIGRP? A query. Right. A linked state update is like what in EIGRP? I'll give you a hint, update. A linked state acknowledgement is like an acknowledgement in EIGRP. A linked state request could also be a reply, yes. I mean, a linked state update could be a reply. But in most cases, it's just considered to be an update. So you're already starting to see some similarities between these protocols. You're already starting to see some similarities. Now, we do have this thing called a database descriptor packet. We'll talk about that in a little bit. That's unique to OSPF. Just like EIGRP, we have a header. Remember, this is sits right on top of IP, so my IP datagram is here, and then my OSPF header. All right? We've got 2 versions of OSPF, version 2 and version 3. The type field is like the opcode in EIGRP. These are the different types that we have. Packet length, that's unique to OSPF. Router ID, we'll talk about what that is. The router ID in OSPF plays a very important role. We saw this idea of a router ID in EIGRP, but we really didn't talk about it because it doesn't really matter that much. The router ID in EIGRP is not really very useful. Area ID, we have areas in OSPF. Checksum, we know what that is. And then you'll notice that authentication is built into the header here as well. Now, we didn't see that with EIGRP, but EIGRP does do authentication. It's just not part of the packet header. Okay? OSPF is carried directly inside of IP. It's protocol number 89. And you always have a 24-byte packet header for every EIGRP packet. So here's the first step in operations. You go ahead and you go into the router, you turn on OSPF on the interfaces. The first thing that happens is it starts sending out these hello packets. It receives hello packets back. That's when we get our adjacencies. Very simple. Step number 1. Neighbor adjacencies are physical in nature, just like EIGRP. So it's only the directly attached routers that become neighbors. Only my directly attached routers become neighbors. All right? What's next? After I've established my neighbor adjacencies, what's next? After I've established my neighbor adjacencies, what's next? Think about EIGRP. What happened after we made our neighbors in EIGRP? Synchronization. We exchanged routes. In the case of OSPF, we exchange these things called linked state advertisements. We'll see that next. So here's my hello packet. This is actually what the hello packet looks like. Now, the first 24 bytes of the hello packet is just the standard OSPF header. So this is actually the hello packet right here. It has a network mask, a hello interval, which is a timer, router priority, dead interval, DR, BDR, list of neighbors. We'll talk about all these concepts as we start to go through the protocol. Most of this stuff doesn't make any sense right now, but we know in general what the hello packet is used for. The hello packet allows us to establish adjacencies. We don't know what a DR or a BDR is yet, but of course we're going to learn that. Okay? All right. Hello packets are sent out using multicast 224005 for all OSPF routers, and special types of OSPF routers use 224006. Hello packets are sent out every 10 seconds. You're going to need to know that for the test. Every 10 seconds. And the dead interval is 4 times the hello timer. So by default, the dead interval is 40 seconds. The hello timer is 10 seconds. I'm going kind of quicker here, right? Because look, the reality is it's the same thing as EIGRP. Maybe the timers are different, but I don't have to go through the whole process of describing to you guys what a hello is used for, what's a dead timer, what's a hello timer, because we've already done all that. We talked about all that with EIGRP. All right? If you want to see the timers, show IP OSPF interface. That will show you the timers that are being used on the interface. Now there is one major difference between EIGRP and OSPF with regard to this timer. Obviously the timers are different, but that's not the major difference I'm talking about. The major difference I'm talking about is that in EIGRP, those timers do not have to match. They can be synchronized. They can be negotiated. But in OSPF, in order for 2 routers to form an adjacency, the timers have to match. That's on the test, by the way. The OSPF hello timers and dead timers have to match in order for routers to form an adjacency. All right? There's other things that have to match as well, but that's one of the major things. We don't have K values in OSPF, so we don't have to talk about K values matching. We don't have an autonomous system number in OSPF, so since there's no autonomous system number in OSPF, we don't have to worry about that matching. So the hello and dead timers are what have to match. Once we've exchanged hellos and we've established neighbor adjacencies, then we start to send these things called link state advertisements. A link state advertisement is basically a route advertisement. It contains the state of all the links attached to that router, as well as what it received from its downstream neighbors. And it floods that information to the next neighbor. All right? So these are like updates. However, there is a big difference. This table up here describes all the different types of LSAs that you can have in OSPF. Okay? You guys are not going to have to know that for the test. You know, in the CCNP you learn about, okay, when are type 2 LSAs generated? Well, type 1 LSAs are generated by everybody. Type 2 LSAs are generated by designated routers. Type 3 LSAs are generated by the ABRs. Type 4 LSAs are generated by ABRs if they're attached to an area that has an ASPR. Type 5 LSAs are advertised by an ASPR in a normal area. Type 7 LSAs are advertised by an ASPR in a special area type, blah, 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 blah. So we learn about all that stuff in the CCNP. Remember I said OSPF is a relatively complex routing protocol. If you thought EIGRP had a lot going on, get into OSPF. It has a lot of stuff going on as well. It's extremely easy to implement. You guys are going to see that in a few minutes. It's pretty much the same as EIGRP. But understanding the concepts gets a little bit more challenging. So once I've exchanged all my link state advertisements, my next step, here's my database. This is your topology table, right? That's where all my routes are, all right? And what do I do against that topology table? I run my algorithm, just like EIGRP, except for in EIGRP, the algorithm is dual. I run my shortest path algorithm and out pops my routes, my best routes. Okay? All right? So it's exactly the same process. Build your neighbors, exchange routing information, put it in your database, run your algorithm, out pops your routes. Excellent. With regard to the metric, now the metric in EIGRP was rather complex. The metric in OSPF is actually rather simple. Very simple, actually. In fact, let me go ahead and draw a diagram here. Get rid of that. All right, let me pull up Paint. I don't have it open here, so hold on a second. Here's how the metric for OSPF works. It's really, really simple. You've got a router, router. All right. You've got maybe a link here. Here's network X. Okay, big X. All right. We know already that which interfaces matter. If I'm going this way from R1, which interfaces matter to calculate the metric to network X?
Egress. Yeah.
Egress, right? So this interface matters, this interface matters, that interface matters. But here's the formula for OSPF. 10 to the power of 8 divided by bandwidth in bits per second. It's not kilobits, it's bits. So all you do is you do a show interface here, get the bandwidth, show interface here, get the bandwidth, show interface here, get the bandwidth, calculate the value for this, calculate the value for that, calculate the value for that, add them up, and that is your metric. It's very simple. So let's say I calculated the metric for this interface is 10, the metric for that interface is 10, the metric for that interface is 10, the overall path metric is 30. We're not worried about the worst bandwidth along the path. We're not worried about delays. We don't multiply by 256. We don't do any of that stuff. It's just 10 to the 8th divided by the bandwidth of the interface in bits per second. That becomes something called cost. C-O-S-T. That is the metric for OSPF, path cost. Okay? So it's actually a really, really simple metric. But simple is not necessarily bad. Simple is not necessarily bad. A couple of points to meet, though, a couple of points. First of all, this reference bandwidth is 10 to the power of 8. That is a problem. I'm not sure why they haven't changed that. But the reason that's a problem is because of the denominator. The denominator is in bits per second. So a fast Ethernet link has a metric of 1 because effectively it's 10 to the power of 8 divided by 10 to the power of 8. Which means anything above fast Ethernet also has a metric of 1 because you don't do any floating point math. You can't have a metric of a half of 1. You have to have a whole number. So by default in OSPF, if you don't understand this concept, you're going to have some issues because if you have gig links or 10 gig links, the router is going to treat that as the same cost as a fast Ethernet link. That's not a good thing. Fortunately, we have the ability to change this value, which we normally do as if we implement OSPF for a customer, we're going to change that to 10 to the power of 10, not 10 to the power of 8. If I change that to 10 to the power of 10, that means that this guy goes up to 100, this guy goes to 10, and this guy goes to 1. That's much better. That's called the reference bandwidth, and you can use this formula or this command to change that reference bandwidth. Right here. Auto cost reference bandwidth. The default is 100, so we would normally just change it to 10,000. Change it to 10,000, you're good to go. All right. That's it for the metric. We already know the rest. Show interface allows us to see the bandwidth. We do that from EIGRP. Only the egress values are used. We knew that from EIGRP. No floating point math. We knew that. All right. That's it. This we'll talk about in the CCNP class. All right. So, a couple of things about single area OSPF versus multi-area OSPF. All right. As I mentioned before, this is our autonomous system. All right. Let me do one thing real quick. Because this is a duplicate slide, basically. Get rid of that junk. From the beginning. No, we're not going back to the beginning. All right, so there's a few things I want to point out about multi-area OSPF. Area 0 is always your backbone. If you're running multi-area OSPF, you always have to have an area 0, period. There's no exception to that rule, and you can only have one area 0. A router that has all of its interfaces in the backbone is called a backbone router. Makes sense. A router that has all of its interfaces in a non-backbone area is called a normal router or a non-backbone router. However, you've got these special types of routers here that have an interface in the backbone and an interface that's not in the backbone. This is called an area border router, which makes sense because it's a router that borders two areas. There's something special about an AVR in that it is the only router in OSPF that you can actually summarize on. Unlike EIGRP, where you can summarize anywhere you want, in OSPF, you can only summarize on an AVR or an ASPR. What is an ASPR? This is an ASPR. An ASPR is a router that has one interface in the backbone and one interface that goes to an external routing domain like EIGRP. This little circle should actually be like right here. This external routing domain circle should go like this. But it doesn't. Okay?
That was an ASBR. AS.
ASBR. It stands for an Autonomous System Boundary Router. So you can see you have a lot more complexity when it comes to OSPF because of this hierarchical structure that exists. This hierarchical structure makes it a little bit more challenging. We're going to focus on single area design in our design. We're going to focus on single area design. All right? So, another aspect that's tested on is the adjacency process between OSPF routers. Now, you guys remember when you were configuring OSPF, when you were configuring EIGRP, what was happening between the routers? You started seeing adjacencies pop up, right? Almost immediately. As soon as you implemented the protocol and the interface, it came up, right? And that's because in EIGRP, you're either not a neighbor or you are a neighbor. But in OSPF, we go through 6 different states: down, init, two-way, start, exchange, loading, and full. That would be 7 states, but we go through several different states. Now, it's not exceedingly important that you understand these states, but we'll go ahead and talk about them anyway. The down state means what? It means that I've sent a hello, but I haven't received a hello back. So I don't identify that there's any potential neighbor that exists. Again, these states are all from the perspective of this router right here. The init state means I've sent a hello, I've got one back. So I know that somebody is trying to initialize an OSPF session with me, and I'm trying to initialize an OSPF session with them. What gets us to the two-way state? Any ideas? What gets us to this two-way state? What would have to happen for 2 OSPF routers to be in a two-way state? They're not fully adjacent. We're not done with that yet. When the link state database is full in each router, no, not that. When the hello is sent and received, that's the init state. We go into the two-way state when we realize that we can actually become neighbors. Because it is possible for me to send a hello and receive a hello, but our timers don't match, we're not in the same area, whatever. There may be lots of reasons why we don't form an adjacency, but essentially 2 routers in a two-way state, the routers recognize each other, and they also recognize that they have the ability to form an adjacency. We haven't formed the adjacency yet. We haven't even exchanged any routing information yet. All we do is we recognize that both routers see each other, and both routers recognize that their properties are such that they can actually become neighbors. So we move from the two-way state to this xstart state, all right? Now, we don't really see a whole lot about the xstart state, but this is where those DVDs are exchanged. Database descriptor packets. I don't really need to get into the detail of that, but basically they're just summary LSAs. Not summary LSAs, but a summary of my link state database. So in the xstart state, I'm doing things like deciding who's going to be the DR, who's going to be the BDR, and then of course you know what the exchange state is. The exchange state is where we're actually exchanging link state information. All right? I'm telling you, hey, these are all the links that I know about. You're telling me these are all the links that I know about. In the loading state, we're actually exchanging the routes. So let me give you an analogy. And this is where OSPF gets a little bit more efficient. You have a very detailed database of link state information. I have a very detailed database of link state information. But there is the possibility that some of the routes that I have, you already have, because you might have learned them from somebody else, and vice versa. So rather than exchanging my entire routing database at once, I'm going to send you a summary of the database. You're going to send me a summary of your database, and then I'm only going to request the routes that I don't have that you have, and you're going to send me those, and then you're going to request, they don't show it here, but you're going to request the same thing. I guess the bottom line here is this whole process, this whole process that we see right here is simply the process of exchanging routing information. Once all the routing information has been exchanged, that's when we're in the full state. The full state means we're fully adjacent, and we can now actually start routing packets. You know what I'm saying? Follow what I'm saying? So, why do we even have this in the slide deck? Because there's literally one question on the test about it. You can decide whether or not you're going to remember all the states or not, or if you're just going to memorize the question. That's totally up to you. All right? Downstate, init state, two-way, extart, exchange, loading, and full. The easiest way to remember it is from the outside in, right? If you can remember the first and last state, you're already halfway there. Down and full, obviously those are going to be my first and last state. Okay? Otherwise, it's just something you just have to see on a regular basis to remember. Why is it particularly important as an engineer to know this? Because there is the potential that neighbor adjacencies don't form, and you might actually get stuck in one of these states. Maybe routes are not being exchanged correctly, so you keep going from the exchange state back to the init state. Or maybe you get stuck in the two-way state. Who knows? So you have to understand how to troubleshoot each of these states themselves. All right. Router ID. I promised we were going to talk about this. First of all, the router ID is used for only one thing. It's used to identify the router within the autonomous system. Not within the area, but within the entire autonomous system. That's what the router ID is used for. So each router in our topology is going to have a unique router ID. Router ID, router ID, router ID, router ID, router ID, etc. Every router within the entire autonomous system has a router ID. Okay? And in OSPF, that router ID plays a very, very significant role. It's extremely important that that router ID is unique. If it's not unique, for lack of a better term, all hell breaks loose. Right? Routers become adjacent, then they go away, then they come back, and they go away. All kinds of stuff happens when you have duplicate router IDs. So you need to make sure that this router ID is completely unique throughout your entire autonomous system. You can make the router ID whatever you want it to be, as long as it's unique. All right? The router ID is written in a dotted decimal format. It's not an IP address. It's not an IP address, but it's written in a dotted decimal format. Okay? It can be an IP address, but I just want to make it clear that it doesn't have to actually be an IP address. Now, there's three ways a router ID can be established in OSPF. The first way, which is kind of the preferred method, is to manually configure the router ID. Go into the routing process and assign the router ID manually. Why is that the preferred method typically? Why is manually establishing the router ID the preferred method? Anybody?
Knowing which is which later on down the road.
Because it's predictable, it's manageable, it's documentable, right? If you're manually configuring the router IDs, then you have control. It's like making your network statements more specific versus less specific. You know which interfaces are going to be part of the routing process. All right? Anytime something can be manually configured, it's going to be better. But let's say I don't manually configure the router ID. If the router ID is not manually configured, then we look at loopback interfaces. By the way, this is on the test, so You need to know this router ID process. If I have a loopback interface, we're going to use, and I should update this, but we're going to use the highest IP address on the loopback. Yes, there. That's a G. All right. What do I mean by the highest IP address? I mean literally 172 is bigger than 10. So if you have 5 loopback interfaces on your router, as long as the interface is active, it doesn't even have to be part of OSPF, but as long as that interface is active, that becomes the router ID. Okay, seems fair. Why would I choose to use a loopback as the router ID as opposed to a physical interface? When do loopback interfaces go down? Are they tied to any physical layer concept?
Only when you show it.
Right. Loopback interfaces are always active. The only time they go down is when the router goes down or if you shut them down. So by using a loopback interface to determine your router ID, it still makes it somewhat predictable because as long as the router's up, the loopback interface is up. But what if we did not specify the router ID explicitly and there's no loopbacks? Then we use the highest IP address on a physical interface. What if I don't have any physical interfaces that are active on my router? Well, if I don't have any physical interfaces that are active on my router, then I don't have a router. You guys agree with that, right? How can a router route if it doesn't have interfaces? So I guess the bottom line is there's always going to be a router ID, isn't there? There's always going to be a router ID. So just to recap, router ID you can manually configure. That takes precedence over every other method. If you haven't manually configured the router ID, then you have to choose from a loopback interface. Highest active IP on your loopback interface. If you don't have a loopback, then what? Highest physical IP. Highest IP address on a physical interface.
Yeah.
Has to be active interface. It can't be a shutdown interface. It doesn't have to be part of OSPF. All right. I'm going to defer this discussion, the DR-BDR discussion, for a little bit later. I keep meaning to change this diagram. It's a crappy diagram. Because I haven't changed it yet, I'm not going to talk about that right now. All right? Which goes to this discussion, goes to this discussion. I am going to come back and talk about this. This is important, but I want to talk about it with respect to our network topology. So, you guys get to do your exercise. Here is the topology. All right? Again, this is similar to a routing topology that you potentially could see on the exam. All right? Potentially a topology that you could see on the exam. All right? So let's take a look at, because I'm going to have you guys kind of do all the configurations together. Let's take a look at the configuration process. First of all, this looks familiar. Router OSPF. Something different though. This number here is not an autonomous system number. It is called a process ID, and it does not have to match on any of the routers. That's on the test also. The process ID identifies the OSPF process on the router itself. It is not an autonomous system number, so it does not have to match on all of the routers. Okay? Router ID. We have chosen to go ahead and assign our router IDs manually. I do want you to do that. The router ID is essentially listed on the diagram. Everybody's dropping off the WebEx. All right? These are all the router IDs, so I want you to set those values. Okay? Oh, Giovanni left. I must have dropped off by accident. What about my network statements? Guess what? The network statements in OSPF are the same as EIGRP. There is a slight difference though. You have to use a wildcard in OSPF. You cannot enter network statements without a wildcard. Follow me? You cannot implement network statements without a wildcard. It's an absolute requirement. And then in addition, we're putting interfaces into areas. For us, every interface is in area 0, so that's pretty simple. That's how you actually tie an interface to an area. If I wanted to make this area 1 and I wanted to make this area 0, then I would just simply put all these interfaces in area 1 and I would put this interface in area 1. So my network statement for this interface would have area 1. My network statement for these interfaces would have area 0. That's literally how you configure multi-area OSPF. So this is in the same folder that you guys got the other lab. This is obviously called the OSPF lab. What I would like you guys to do, and also I broke it, there's one link that's broken. See if you guys can figure out why it's broken. I want you to go through and implement OSPF. Now, I did in this time, in this book, I've given you the configurations for every single router. On both of these pages, every single router's in there. Okay? So essentially, you just have to follow what's in the book. But you should understand it at this point because of how much time we spent on RIP and EIGRP. All right? All right, gentlemen, I'll let you guys do that for a few minutes, and then we will continue on like we did with the EIGRP, going through the exercises.